All right, let's finish this chapter 12 off with this third video. So last class or last video, I suppose, we found this linear regression line, this linear model. But why do we even find models, right? Uh, it's to predict data for X values that we don't have known data for, right? So there's a whole bunch of models. There's, exponential models, logarithmic models, and but what we're dealing with is that linear model. So it says here, understanding the trend/shape of the scatter plot allows us to make predictions, right? We have that predicted Y. This means that we can produce an educated guess, a response value for the explanatory values that weren't observed. So we see this here, and I understand that we already know 130. But there could have been something that went wrong with that specific data point. So we actually want to know what happens, like what does the model say should happen at 130? If I were to do it again at 130, what is the most likely time it would take? So from before, we know that y hat equals 0.01x plus 5.53. And to make this prediction, which is something we'll do, y hat equals 0.01 times 130 plus 5.53. And that gives me, as I put that in my calculator, 0.1 or 0.01. Oof, sorry about this. 0.01 times 30, and I'm sure you can do this as well. 6.83. And that's how we'd make predictions, right? So we do this all the time. You see this all the time in any sort of scientific community or scientific topic, the predictions, what's going to happen in the future, what the modeling tells us. So most of the time, we don't do what we just did, right? We don't predict values inside of our interval. That is called interpolation. Most of the time, what we care about is, okay, I see this trend. What happens at 200 feet? What happens at 220 feet? This process is called extrapolation, something you've probably heard before. So for the example above, we are extrapolating. So that's the whole goal of modeling, is to extrapolate data. So I can start talking about, drill times at 200 feet, maybe 220 feet, even 250, 275 feet would be reasonable. But I can't make a prediction at 400 feet because it's too far away from my data. So that's something I want to really be careful about. And another really important topic in stats that we'd want to take home is don't extrapolate too far. So here's a fact we want to write. We cannot extrapolate too far outside the range of our data because the model may change. The model may change. So, 200, 250 feet, 275 feet, maybe the Earth is just still getting more compact and we don't have a problem. But maybe at 400 feet, 450 feet, the molecular structure of the Earth, of that crust, of that dirt is changing because, it might be hotter because it's closer to the Earth's core. So it might take longer or shorter to drill, right? Maybe it's easier to drill through warm rock than it is through cold rock. So, as a general rule, and this isn't official, this isn't like something that all scientists have agreed on, you don't want to extrapolate past 1.5 the range of your data. So, if I have 200 feet of data, maybe I can go up 100 more feet, maybe. And again, that's not an exact value, but anywhere in that 1.5 range, we're starting to get, iffy. And this happens in real life. People do this all the time in the news. Scientists do this to maybe lead you toward a certain conclusion, right? So this happened recently. Maybe, many of us weren't paying attention in the news, and that's okay. We were a bit younger. But when COVID hit, in that first month, they were making some crazy predictions for August. COVID hit right around March, April. And they were saying it's going to be this amount of deaths in August, in September. And I'm looking at this and wondering how are you figuring this out? That is statistically irresponsible to do. To have 1 month of data and predict 3 months into the future. It's very irresponsible to do. But they were doing it because, and for whatever reason, that's a whole nother class you might want to go into why they were doing this. But mathematically, statistically, scientifically, it is irresponsible. Whereas now we got 4 years of data. If they were to predict something 3 months, even 6 months in the future, they've probably got a pretty good idea of what's going on, right? Because they have the data, they have the base to support it. So a question that may be asked in the future is, can we make a prediction at this X value? Not what is the prediction, can we? And if it's close to your data, sure. If it's far away from your data, then no, maybe not. So anyways, that's that there. Just basically 12.5 is, hey, here's a prediction and be careful when you predict. Sweet, sweet. 12.6. So if you remembered last class, we mentioned, hey, I know we're talking about linear models. I know we're talking about the linear strength, but can we even do this? Is it even appropriate? Because is our data linear to begin with? The main way we do this is with residual plots. So residuals play an important role in determining the adequacy of the linear model. In fact, plotting all the residuals is useful for the following purposes: to determine whether a linear model is appropriate, to describe the relation, and to check for outliers. A residual plot, which is something we're going to learn how to make, a residual plot, which is a scatter plot, but on the y-axis we have the residuals instead. So on the vertical axis, we have residuals, and keep the x-axis the same, determines if the linear model is appropriate. To describe the relation to the data. How do you do this in a calculator? So let's write it down first. We're going to run linreg. Ax plus b. Find that model. Find that, y hat equals ax plus b. Find the r, just so everything's recorded in your data. Then we're going to go second, y equals, and then choose scatter plot. Running out of space, so I'm going to go here now for the steps, choose scatter plot. Put xlist in xlist. I know that sounds weird, but that's what it's called. And then for ylist, we're going to go second stat resid. Second stat, and then all your residuals are recorded, resid. And then zoom 9 for zoom stat, right? Zoom 9. So to comment on appropriateness, the residual plot must. This language was a little bit weird in this notes. So here's what we're going to say. So ignore that line. If a pattern is clearly observed, and we want it to be very, very obvious. Observed, a linear model is not appropriate. Not appropriate. And then vice versa. If no clear pattern, and we want this clearness clear, it's going to be a very, very obvious pattern. If no clear pattern is observed, a linear model, is not appropriate. Or I'm sorry, is appropriate. Is. So it's this backwards business. And what the residual plot does is it exaggerates nonlinear patterns. So if there was a secret pattern that you couldn't see in the original scatter plot, this residual plot will exaggerate the pattern. So if you see a pattern, that pattern is nonlinear. So linear model is not appropriate. But if there's no pattern, linear model is good. So yes pattern, no linear. No pattern, yes linear. It's kind of uncomfortable at first. And then just real quick, to identify an outlier, the residual will lie far from the rest of the plot. And it'll be very, very clear. So I wouldn't worry about that. But what we want to do to finish off this chapter now, real quick, put this in two lists side by side. Put this in two lists side by side. And we'll go through the steps together. Because these steps in purple here are kind of confusing. So we need to really do it once for it to make sense. And then always be able to reference this video when we're doing it. So go ahead and start entering that data. I'm going to switch the camera around. And of course, press pause if need be. Okay. So hopefully you press pause and started entering. And here's where we are. Mine are in L5 and L6. It doesn't matter what list you're in. But what I need to do first is run linreg, stat, calc, go to 4. And since mine are L5 and L6, we got to do that. Boom. There it is. We have an R value of 0.07, a very weak R value. So we can imagine what's about to happen. And then we start the steps that we have written down. Second y equals. Second y equals. Click on the first one and choose scatter plot. You put your X list, your explanatory variables, which is L5 in here. And then when I'm on the Y list, we're going to go second stat. And then you'll see that resid button. Then from here, you're going to go zoom 9. Okay, so something has told me I've entered my data wrong. So let me pause real quick because you probably got different R values. And look at my data. Oh, and that's what happened. You can see, I'm not even going to press pause. You can see I entered 0.01 instead of 1000. So I guess you can watch me do it again real fast. Stat, calc, linreg, calculate. Okay, so R is negative 0.99. That makes more sense. But when I do the scatter plot, zoom 9, look at this very, very clear, obvious pattern. And on the test, it will be just about this obvious if there is a pattern. It might be upside down. It might be the other way, going from here down. But for these notes, what I'd expect you to write, or a sentence or an option I'd want you to choose is, let me share my screen, something like this. A linear model is not appropriate since there is a pattern in the residual plot. And my pen has just gone funny. There is a pattern in the residual plot. And that would be the answer to this question. Is the linear model appropriate? Now notice there was another question. Is there evidence that the data has a linear association? Yes, there most certainly is. Remember, when you ran linreg, and I'm double checking it right now, when I ran linreg, I got an R value of negative 0.99. R equals negative 0.99. Yes, there is a strong negative, very strong, honestly, a strong negative linear association between day, or between time and weight, really, between time and weight. Oh man, I don't know why that's not deleting, but between, just cross it out, time and weight. Cool. That's what the R value says. But we further analyze and we figure out that, oh, linear model, definitely not appropriate, right? And that makes sense because if you've taken a chemistry class, we know that radioactive decay decays exponentially fast. So there's an exponential model there, not a linear model. So something to think about that. So as a review, what I hope you would do right now is press pause, look at your drill data, and then let's talk about the appropriateness of that. So go ahead and press pause. I'm going to also press pause, and let's see what happens. So hopefully you notice, whoa, sorry, a bunch of things just got closed. Hopefully you notice that there is no pattern. So yes, a linear model is appropriate. Is appropriate since a linear model, nope, sorry, since, and my delete is not working here, since there is no clear pattern in the residual plot. That's what we're thinking. Right? And the residual plot, just so you know, we can look at the little camera, is here. Sorry, my computer's being a little bit weird right now. Oh, I understand. So you can look at my camera and you can see no pattern. They're just scattered randomly throughout, and that's what we expect. So anyways, that's chapter 12. This is a more difficult chapter. Hopefully we do well with this. This is all making sense, but I will mention that typically in the terms of the course, this is one of the more difficult chapters. This is maybe third most difficult. So give this one a little extra TLC. Pay a little bit more attention to this chapter for our next test. But anyways, hopefully everything's made sense. Be sure to email me or come see me on office hours. Have a good one until next week.